In this narrated PowerPoint, we're going to talk about using the normal approximation to the binomial for counts, usually just called the normal approximation to the binomial. Now, I want to tell you, quite frankly, this is of historic interest only. Before we had software, before SurfStat and other online calculators, before even TI-80X series calculators, people used the normal approximation to the binomial. My goal is that if you read an article that uses the normal approximation for counts, you can check if the answer is close enough to trust. Now, you never have to do this. And quite frankly, given the tools we have today, it's a really good idea not to. But this is featured in section 9 in the reader. Baldi and Moore discuss it very briefly on pages 298 to 300 in chapter 12, and quite frankly they drive me nuts because they save the best real deal method for one of the exercises, but occasionally they do put important things in the exercise. So here we go. We are still in the situation where we think we know the population proportion P. And given N and P and a probability we need to find, particularly something like the probability X is greater than or equal to 75, here's how we can do it. Step 1, check the conditions for using the normal approximation. Okay, so in order to do that, we have to compute the expected number of yes and no, as we saw in the last PowerPoint. And we ask the question, are both n times p and n times 1 minus p at least 10? Preferably, we'd like them to be a good bit bigger than 10. And if the answer to that question is yes, the normal approximation is okay. Step 2, if you're okay on the conditions, compute the expected number of the count, and actually you already have that because it's n times p. Compute the standard deviation of the count, n times p times 1 minus p. So if we've got that set up, to get the most accurate estimates of binomial probabilities, we're going to use something that is called the correction for continuity. And we're just going to explain this informally, looking at a binomial spike plot. So we've looked at this before. Here's a nice binomial spike plot. The thing about the binomial spike plots is they only put the probability mass on the integers. Okay, the reason it's a spike plot and not a bar plot is the only possible values of the count are these integers. But we're talking now about using the normal curve, a continuous distribution, to approximate binomials. And so if you do an approximate binomial calculation, the binomial will give you a positive number for x equal to 15. But the normal curve, remember, is kind of weird because, like all continuous distributions, you're forced to say that the probability that x is exactly equal to 15 is a 0, because for continuous distributions, probabilities are areas under curves. So what we're going to do is we're going to say, okay, in applying the normal approximation to the binomial, we're going to approximate the binomial probability x equal 15 by a normal curve area between 14.5 and 15.5. And if we do that, we're going to be able to get a number that's not 0, which is going to line up better than if we don't. So how this is going to work is pretty simple. We're going to do it in an example. Here's a story from Baldi and Moore that has to do with postmenopausal women with low bone density, and they tell us that for the U.S. population, the proportion is 40%. And we've done a couple other things with these data before in our probability work in week 2. So now we're taking a look at this for the normal approximation to the binomial. And they tell us in this problem that a particular practice group has 248 menopausal women and that 82 of these women have low bone density. And the question Baldi and Moore asked us to look at: does the percent of women in this practice with low bone density look comparable to the U.S. population? And this is on its way to the kind of inference questions we're going to learn how to answer in week 6. So just to think about it, could the difference between our practice's proportion, which is about 0.331, and the U.S. population of 0.40 just be chance variability? Because after all, we've only got 240 women, so we wouldn't expect our proportion to be exactly 40%. The alternative to this that we might be interested in: does our practice have a lower percent of women with low bone density than the U.S. population? And again, we looked at this when we were looking at the Surfstat and Stata binomial. So we're using the same example to take a look at the normal approximation. So basically, we already know the answer. We found that the probability of 82 or less in a sample of 248 with the p of 0.40, if we write this out as a sum, I going from 1 to 82, 248 choose I, 0.4 to the I, and then 6 to the power 0.248 minus I, we found out that this was about 0.0145. There's the Stata binomial function that we use to get this sort of probability. So I'm rounding it to 0.0145. Now, to use the normal approximation, first thing you have to do is work out the expected number of yes and no. And for our sample size of 248, probabilities of 0.40 and 0.60, both of these expected counts are well greater than 10. So we're going to be okay if we want to use the normal approximation. We don't have to. We already know the answer, but let's see how this works. Okay, we've got the mean for the count 248 times 0.40 or 0.992. We need to get the standard deviation. Square root of 248 times 0.4 times 0.6, or about 7.7. Now the thing we're going to do to use the correction of continuity is we're going to think about what happens around that upper limit of 82. We're actually going to find the area under the normal curve less than 82.5. Why? Because the probability x is equal to 82, the last term in that binomial sum from 0 to 82, if we do the correction for continuity, it's going to be the area between 81.5 and 82.5. So that's how we're going to apply it. So for the normal approximation, our z-score looks at 82.5 compared to the mean of 99.2 for the count, if it's really 40%, divided by a standard deviation of 7.7. We're going to get a z-score of about minus 0.217. The area under the normal curve lower than minus 2.17 is about 0.015, which is pretty close to the exact answer, the 0.0145. So the normal approximation to the binomial does work here. Now Baldi and Moore ask an interpretive question, and they expect students to be able to apply these calculations, whether we're doing the exact binomial or the normal, to say, what are you going to suggest at the next physicians meeting? So this is a little preview of how we're going to use this for inference, and I think it's good to keep thinking about this. So if we think about all possible random samples of size 248 from the U.S. population, the calculations we've just done tell us that less than 2 in 100 of these samples are going to have 82 or fewer women with low bone density. So, if the population of 40% is applicable to our specific group practice, observing 82 or fewer postmenopausal women with low bone density would be a pretty rare event. Not an impossible event, but less than 2 in 100 for probability. So what we're going to conclude is that we've got evidence that our practices postmenopausal women have a lower probability of low bone density. What do we think the probability for our practice really is? Well, the sample proportion, 82 out of 248, is about 0.33. So coming up soon, in week 5, how are we going to calculate a margin of error to report along with this estimate of 33%? Because it's really important not to just say, yeah, we have evidence that our practices proportion is lower, but to try to do our best to quantify how much lower it is. So the normal approximation to the binomial is a useful thing to know about, mostly for reading papers. If you're calculating proportions for counts, you never have to do this. We're going to see in the final narrated PowerPoint for this week, it's a little more useful to know the parallel normal approximation for proportions. But for counts, we're going to de-emphasize knowing the details of how to use what we've just talked about, partly because we're in such a fast-paced, intense course. So we're almost done with the material for week 3. We are done with the material for week 3. We're almost done with the material for week 4. There's one more section to go.